Hello once again. Thanks for joining us. This is Space Nuts. My name is Andrew Dunkley. Great to have your company. And in episode 375, we will dedicate the entire show to audience questions, and we've got a bunch. We're going to be looking at the Big Bang and the gravity associated with that. We'll also be looking into what the universe might be like if there was no such thing as dark matter. I love the what-if questions. And a carbon star called La Superba. Somebody's asking a question about that. We've got a whole bunch of questions. We better get into it right now on Space Nuts.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me again to discuss all of that and so much more is Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How are you today?
I'm very well, sir. Feeling relaxed. Judy and I did a 4-night cruise out of Sydney last week, just up to Moreton Island and back. Unfortunately, the weather was not kind to us, so we never got off the ship. So, but, that's okay. There's always plenty to do on a ship. And we had a lot of fun. It was nice to just have a bit of a breather and just not have to worry about anything. No bed making, no cooking, just get up, eat, go to sleep. That was pretty well the bang.
and check out watches as well, of course.
Go to the watch shop. Yes, I've that's become a regular thing when I go on a cruise ship. I don't know why, because they cost 10 times more than if I go into a jewelry shop. Yes, but I've just become fixated with watches, and I think it's because my grandfather was a watchmaker. And when I was growing up, I used to go to his shop and watch him out in his little workshop out the back fixing watches in the days where you actually did fix them. And I was just fascinated by it, just thought it was amazing. Because during World War II, he was an instrument fitter for the RAAF. And so he was out around the New Guinea Islands where the Japanese were occupying. So, pretty tense times. Came back and got an apprenticeship as a watchmaker and, I even visited the first shop he worked for in Griffith when we were down there.
Oh, all right. Okay. Yeah, he'd sail through watchmaking with that instrument fitting background.
Oh, yeah.
Because certainly in those days, the mechanics were much the same for watches as for aircraft instruments.
That's why this watch I've got is fully mechanical. No batteries, no winding it up. It's automatic. It just winds itself. I've always been fascinated by that. Yeah, it's good gear.
I just as an aside, so during the late 50s and early 60s, in the United Kingdom, there were these wonderful government surplus shops, and there was one in particular that I used to hang out in. And I used to regularly buy lots of optical instruments, which is how I, got hooked on the way lenses work and things like that. And it was all about trying to make telescopes for astronomy. But they also sold aircraft instruments, surplus aircraft instruments. And pulling one of those to bits was a lesson in watchmaking, basically. Yeah. It was the same sort of stuff inside. It was remarkable.
Yeah, it's so intricate too, because he used to sit there with his little thing attached to his glasses so he could magnify what he was
watchmaker's eyeglass.
Yes, exactly. Yeah. Quite astounding. Yeah. All right, we better get stuck into whatever we're doing today, Fred, and that involves audience questions.
Well, we could just keep
talk about watchmaking.
We could just keep. Well, it's just involve the audience as well. They probably want to know about watchmaking.
Let's go to our first question. This comes from a familiar voice. His name is Rusty.
Hello, Fred and Andrew. It's Rusty in Donnybrook. Now, we know it's common usage now that common knowledge that gravity affects the passage of time, and we have to make adjustments for it with our satellite navigation. So taking that a step further, black holes. As we're closer to black holes, a recent movie highlighted that time slows down, but the event horizon, there's no physical reason why at the event horizon time wouldn't slow down further as you approach the singularity. And finally, when you get to the singularity, the point of infinite density, time would stop altogether, wouldn't it? So one more step. We go to the Big Bang. Before it expanded into the universe we know, it was very tiny, and all of the matter was squeezed into a very tiny little pinhead point. So wouldn't gravity have slowed time down to an incredible degree? And what we measure now as milliseconds or silly seconds would have perhaps taken very much longer as we would measure it now today. So could the infant universe, the embryonic universe, have taken trillions of years to break out of its pinhead size? That's the question. Cheers, guys.
Thanks, Rusty. You got there eventually. Could the early universe have taken trillions of years to break out of its infinitesimal minusculeness? If that's a word.
And the answer is yes, if you could have observed the universe from the outside, because it's all about reference frames. That's the thing. It's why time, to an outside observer, time appears to slow down for somebody falling into a black hole. And in fact, it's when you cross the event horizon that time appears to stop altogether. Excuse me, I've got a time-dilated frog in my throat. So the bottom line is it's about reference frames. But I think Rusty's point is kind of well made, because the same thought has occurred to me that, we talk about the period of inflation. Now, I'm going to get these numbers wrong, but it's something like it started when the universe was 10 to the minus 33 of a second old and stopped when it was another 10 to the minus 33 of a second old. And those are just ridiculous timescales. But if you were in the privileged position, and I think there's only God can do this, but if you were looking from the outside at the universe, then it might look like trillions of years. That's right. But for those of us involved directly with the Big Bang, which is everybody in the universe, it was a very short, it might have looked like a long time to somebody outside, but it's a very short time in the time dilated rest frame. That's the way to be precise about that. There is some, we talked about it recently, Andrew, some work that's been done here in Australia, which involves looking at distant quasars, and there's a sort of clock signal that you get from those. And these astronomers showed that, yes, we are looking from the outside effectively at the time regime that those quasars were in, and there is time dilation taking place. You can demonstrate that what we see looks slower than what it actually was because of gravitational time dilation.
It's just so hard to get your head around.
Yeah, you're looking puzzled there.
Yeah.
I don't blame you.
Yeah. Just the idea that the universe existed for trillions of years on a minute scale before the Big Bang. I mean,
well, that's another possibility.
Well, you can't prove it, but it's just that's just a massive time scale to try and absorb, to try and figure. When we've talked in the past about what was there before the Big Bang, the answer is nothing. So there were trillions of years of nothing, and then there was something.
No, there wasn't trillions of years of it because time didn't exist either. So there was nothing, not even time.
Not even time, right? See, my brain doesn't like this.
No, I don't think anybody's brain does, actually. I think, that's... in that regard, watchmaking's a lot more straightforward than relativistic cosmology.
Yes,
because none of it is intuitive. You've really got to go into the mathematics and sort it out that way.
But the big question is, if I did get sucked into a black hole and cross that threshold where time stopped, would my watch keep working?
It would. Yeah. Your watch wouldn't know any difference, apart from being spaghettified. That might interfere with the works.
Let's just pretend that didn't happen.
Certainly muck up the self-winding mechanism.
Indeed. All right. Have we given enough attention to Rusty's question? I think we've covered it. I always try to go on and you say, hang on, there's one more thing.
Yeah. No, in as much as we ever cover anything, Andrew, I think, we've covered that.
All right. Thanks, Rusty. Let's move on to our next question.
Great.
This one comes from Michael. This is a pretty deep thought question as well.
Hey, guys. This is Michael calling from Toronto, Canada. I just have another question for you guys. I've been thinking, we usually hear about Einstein's E equals mc squared as sort of a conversion from mass into energy. So I understand that it's probably a bidirectional kind of conversion that could happen, but I don't usually hear much about energy being reconverted into mass. Are there any situations that you're aware of where this does come up? So I was thinking maybe this could explain dark energy or dark matter. Say maybe there are some kinds of energy like gravitational energy, or maybe even the energy that's produced from photons in fusion in stars. That's somehow responsible for what we perceive as dark energy or dark matter. What do you think? Thanks, guys.
Thank you, Michael. Like I said, a pretty deep thought type of question. Basically, turning energy into mass. Any evidence of that, and how would it work in a universal state situation?
The probably the most well-known example of energy being turned into mass is the Big Bang.
Yeah,
because that started off as as just energy, I guess photons, and eventually became it became a kind of super particles. In fact, the first set of this is laws of physics, which is slightly different. There was one of the first things that happened was the break between the electroweak force, which is what holds nuclei of atoms together, and the electromagnetic force, which is photons. That sort of happened in the early Big Bang period, but that's more a sort of separation of forces rather than energy being turned into mass. But energy did get turned into mass. That's kind of how it worked. But if you check up online, it's a rare phenomenon. But there are examples. I think we've actually talked about them before, Andrew. It's quite a long time ago. But back in 2021, the Brookhaven National Laboratory in the USA, basically they issued a press release entitled "Collisions of Light Produce Matter Antimatter from Pure Energy." And this is an article that you can read. It goes into details about particle collisions in the relativistic heavy ion collider, the RHIC, which is a US Department of Energy Office of Science user facility for nuclear physics. And it's at Brookhaven, the DOE's Brookhaven National Laboratory. So what they've done is they've basically collided essentially beams of light. I might actually read the beginning because that explains it a lot better than I can. Mm-hmm. They've produced definitive evidence for two physics phenomena predicted more than 80 years ago. The results were derived from a detailed analysis of more than 6,000 pairs of electrons and positrons produced in glancing particle collisions at the RHIC and are published in Physical Review Letters. The primary finding is that pairs of electrons and positrons, in other words, particles of matter and antimatter, can be created directly by colliding very energetic photons, which are quantum packets of light. This conversion of energetic light into matter is a direct consequence of Einstein's famous E equals mc squared equation, which states that energy and matter, or mass, are interchangeable. Nuclear reactions in the sun and at nuclear power plants regularly convert matter into energy. Now scientists have converted light energy directly into matter in a single step. And so you can read more about that. But what that tells you, Andrew and Michael, indeed, is that we're talking about something that's not a commonplace phenomenon in the natural world. where we're seeing the other process happening all the time in the sun, matter being converted into energy. But to convert energy into matter is a rarity, but it can be done, as we've just heard.
All right, Michael. So the answer was yes. Could have saved a lot of time if we just said that, but
Good.
yes.
Yeah, could have done. Yeah.
Very good question. Very, very good question. How would that relate to his question about black holes and dark matter, dark energy? Any relationship there?
Yeah, sorry, I should have followed up on that. Well, the thing is that dark energy, our understanding of dark energy and dark matter, they take into account this rarity of such kind of reverse engineering taking place, of creating mass from energy, purely from energy. And I think I suspect it's not something that has been overlooked by the cosmologists involved, the possibility. But I think it's such a difficult thing to achieve that it might be something that is essentially ruled out by the theory. And what I was going to say was we kind of, what we don't know about dark matter and dark energy is what they are. We can kind of guess where they came from because the Big Bang lets you look at the kind of energy budgets that are there, and you basically get what we see around us today. If you do the mathematics, universe that's kind of 3/4 dark energy, about 20% dark matter, and 5% everything else.
Yeah.
So it's more about the puzzle with dark matter and dark energy is how they, what they are, what particles carry dark matter, what subatomic particles as well, because you can look at it that way, would carry dark energy, and we don't know the answer to that. Although
Okay.
you can sort of work out where they came from, if that's a paradox that you can deal with.
All right. Thank you, Michael. Yes, and maybe, probably not, don't know, I think, were the answers to your question.
It's the same answer we always give.
Yeah, it is, pretty much. Lovely to hear from you, Michael. Hope all is well in Toronto. Peter has emailed us a question. Peter is from Sydney and a proud patron. So thank you very much, Peter. Appreciate your support of Space Nuts as a patron. He says, money well spent. Look, it's there in writing. I'm surprised but delighted. Now, he asks, I'm praising his question because it was quite long. What if the universe evolved from the Big Bang without any dark matter? Apart from probably halving the number of questions from listeners, what other effects would there be? Could galaxies still form but maybe rotating at a lower velocity so they don't fling apart? Would they still have spiral arms and all the other shapes and sizes they come in? Would solar systems form in a different way? Would we still have galaxy clusters? And what about black holes? Surely dark matter is not the only mechanism in the universe that has to coalesce hydrogen. Or am I wrong? If the above is no, I can only assume that the universe would just be an ever-expanding soup of hydrogen and helium atoms. Looking forward to your answer. Toddy. Thanks, Todd. I love what-if questions. What if there was no dark matter or dark energy or any of that stuff?
I thought that was from Peter, not Toddy.
Peter. Well, he calls himself Toddy, but Peter Todd is his name.
Right.
Sorry.
Peter Todd, right. Now you see, you missed that bit. That's great. Nice to hear from you, Toddy. I always have quite different pictures in my mind when I think of a toddy. It's a mixture of water and whiskey that is got honey in it, and it's what gets you through a bad cold. Especially if your whiskey is something nice and peaty like Lagavulin. Anyway, moving on to other things. So it's a great question because that's exactly the issue that the proponents of MOND have to deal with. And MOND is, which we've talked about many times, is this alternative theory that gets rid of the idea of dark matter. modified Newtonian dynamics, Mordechai Milgram's contribution to the world of physics back in the 1980s when dark matter was first being recognized as a reality. He didn't like the idea and looked at the idea that perhaps our understanding of dynamics was wrong, the way accelerations take place at very, very low levels of acceleration. And he developed this theory of MOND, modified Newtonian dynamics, which has merit, as we know, because we've got friends on Space Nuts, notably Peter Verweyen, whose PhD thesis is on exactly this topic. And Peter talks to us from time to time. So MOND certainly has some useful attributes, but I think one of the things, now Peter might well be able to correct me on this, and I'm talking about Peter Verweyen now, not Peter Todd, but I think it struggles to make galaxies in the early universe because of exactly what Toddy has mentioned, the fact that we think the dark matter provided a framework that basically gravitationally attracted the hydrogen and made stars and galaxies by that acting as a kind of nucleus for gravitational attraction. And yes, it would be possible to imagine a universe that never formed stars and galaxies, and it would indeed be made mostly of hydrogen and helium, with not much going on. So I think that is still an issue for MOND. But we might hear from Peter that there are answers to that. But it's a great question, and like so many of the questions we get from Space Nuts listeners, it's right at the cutting edge of research.
Yeah.
Todd is asking questions that we really probably don't properly know the answers to.
No, but it doesn't stop people wondering. And it's the fact that we wonder that leads us to investigate, that leads to ultimately answers in some cases. Be a fair point.
Yes, we hope.
Yeah, we hope, yes.
Yeah.
It just brings up more questions, which is quite common too.
Well, that's the other thing that happens as well. That's right.
Yeah. All right. Thanks, Peter, or Toddy, as you seem to like to be called. Appreciate your question. Thanks for sending it in. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson. Let's take a little break from the show to tell you about our sponsor, NordVPN. And I'm pleased to be able to tell you that Nord has got a new offer available to you as a Space Nuts listener. Now, I might add that you get exclusivity with this plan. This is just for Space Nuts listeners on the special URL, nordvpn.com/spacenuts. What they're offering is with every purchase of a 2-year plan, you will receive 4 bonus months on top of what you've already bought. And that includes all their plans, their standard, their plus, and their complete plans. And all you have to do is go to that URL to find out more about it. It's a fabulous deal, and it's something that is available right now as a Space Nuts listener. Now, I've been using NordVPN for, it'd be well over a year now. I got everything. I got absolutely everything because I love their interface. I love the simplicity of it. I love its speed. It's high-speed VPN. I've noticed no lag whatsoever in using their VPN service, and it protects me from spyware, hackers, spammers, and not forgetting the censorship issues that you sometimes face, and that geo-blocking as well. You can deal with all of that with NordVPN. But you can also get malware protection. You can get the tracker and ad blocker, the cross-platform password manager. That's my favorite thing. The data breach scanner. And if you want to save space on your computer hard drive, you can use NordVPN 1 terabyte cloud storage. Just put all your stuff on there. Very easy to access and protected. You'll never lose it, unlike your computer completely dying and corrupting the hard drive and it's all gone. There's also the next generation file encryption. Now, there are multiple plans. You can get the basic plan on the monthly, yearly or 2-yearly deal. Obviously, the longer you go, the cheaper it gets. There are big discounts on at the moment, leading up to Black Friday, and you can take advantage of that right now. As a Space Nuts listener, this deal is exclusive to you at nordvpn.com/spacenuts, nordvpn.com/spacenuts. You'll get an introduction page and then click on Get the Deal and find out all that you need to know and all the plans that are available right now with that extra 4 months. And of course, don't forget their 30-day money-back guarantee. That's nordvpn.com/spacenuts. Now back to the show.
3, 2, 1.
Space Nuts.
Okay, Fred, let's go to another audio question. This one I was particularly interested in because I think we talked about this not so long ago. This one comes from Doug.
Hello, Dr. Watson and Mr. Dunkley. This is Doug Stoneback from Boise, Idaho. And I was just wondering, we were looking at a carbon star called La Superba. It's a red giant. And just wondering if, or one, this turns into a planetary nebula, would it show the same color because of its richness in carbon in the atmosphere? Are there any planetary nebulae that came from carbon stars? And thirdly, in regards to the blue snowball, the blinking planetary, and the Cat's Eye Nebula, of course, they're all a bluish and turquoise type of color. Is that due to their atmospheric makeup? Could it possibly be methane, as in Neptune and Uranus? I'd love to know the answers to these questions so I can pass this along to the public. Thank you. And have a great day and keep up the fabulous work.
Thank you, Doug. La Superba, I suppose we should start by explaining a bit about it and what a carbon star is, and then we can sort of move into the spectrums.
Yeah, indeed. So it's a star. I'm interested to know actually whether Doug has observed it because it's let's see, I think it's fifth magnitude. It's a star that's visible to the naked eye, not particularly so from our latitude here in the southern hemisphere because its declination is 45 degrees north, which means that it's a northern hemisphere star. It's in the constellation of Canes Venatici. And in fact, it is Y, Canem Venaticorum. There you go. The hunting dogs, Canis Venatici. And that's a northern constellation. It does cross our northern horizon here in Australia, but not for long. And so it's not one that would be well known. And in fact, at that zenith distance, in other words, that low in the sky from here, a fifth magnitude star is probably not going to be that visible to the naked eye, especially if you're anywhere near city lights. But it's called La Superba, and it was named by an Italian astronomer in the 19th century. His name was Angelo Secchi. He called it La Superba because of its beauty, and its beauty comes from the fact that it's a very red star. In fact, it's one of the reddest stars known, and it is exactly as Doug has mentioned. It's a carbon star, and carbon stars have a richness of carbon in their atmosphere. So this is a star that's it's slightly bigger than the sun in terms of its mass, but it's evolved into a red giant. And in fact, one of the estimates of its diameter is effectively bigger than the orbit of the Earth, so around the sun. So yeah, it's big. And so what you get is basically you get a core of carbon and oxygen, within the star, this is kind of the old age of stars, similar mass to the sun. But the hydrogen and helium burning continues, but it's in shells sort of outside the core. And basically, though this convection takes place that dredges up the carbon from the core. There's carbon and oxygen in the core. The carbon's dredged up into the outer atmosphere, and it forms carbon monoxide and other carbon compounds. And basically, you get absorption of the light from the still burning hydrogen in short wavelengths. In other words, it turns red, and that's so. It's a red giant star at a particular phase in its evolution. It's already got a shell of stuff that it's ejected, and you can sort of detect that because of, once again, of the spectrum. But eventually, that will turn into, exactly as Doug says, a planetary nebula. Now, I'm not sufficiently familiar with the details of planetary nebulae to understand, or at least to carry in my head where the different elements come from that are in planetary nebulae. They clearly come from the star itself through the nuclear processes that have taken place while the star was in its normal life. But what's happened with a planetary nebula is that basically the star has cast off its outer layers, and the core itself has turned into a white dwarf star. It's a white dwarf which is highly energetic, collapsed core of a star, which is pretty bright and very, very hot, hence its colour, and will last a long time before it eventually turns into a black dwarf, which is what most of the stars that we see around us are going to do in the distant universe. But Doug's comments about the materials in the tendrils of these planetary nebulae, which are only called that because some of them look like planets. They're not. They're just shells of gas, often with quite complex morphologies. They've got very troubled-looking appearance. I can't comment on the details of that, but I could, I'll try and put some detail on that for the future. But Doug could be right about, for example, methane being in there, because these things are cool enough that molecules can form. The hot bit is the white dwarf at the centre, but it's cooler in the edges. So there's probably molecules which can only form in relatively cool conditions. I'll check that because it's an interesting question. What elements and molecules you get in planetary nebulae?
Okay. All right, Doug, we'll leave it there, but there'll be more to come. But thought-provoking question, and thanks for sending it in to us. We'll move on to a text question now from Dylan. He said, "Hi there. I have a fun what-if scenario for you to think about. Imagine a world where every space agency had an unlimited budget and zero bureaucratic hurdles starting from the 1950s or even earlier. In such a scenario, how advanced do you envision not only space technology, but all technologies to be today? Could NASA have established a presence on Mars in, say, the 1990s, maybe asteroid mining in the early 2000s? This concept resonates with the TV series For All Mankind, where the space race continues at full throttle and technology is pushed and milestones are achieved that have not been seen today in real life. I'd be interested in what you both think. Cheers, Dylan." I love what-if questions. So we've got a situation, Fred, where there is no limit. They can spend as much as they like. There are no bureaucrats or politicians to slow them down. What would the world be like today in terms of space exploration and development?
Well, I think Dylan's right, actually, and I think you probably think that as well.
I think it to a certain degree. I think what they portray in For All Mankind, and the new season's just about to come out on Apple TV, by the way, I think it's showing the extreme end of the possibility, but I don't think in real terms we would have achieved what they've achieved in that series as a science fiction show in real terms today, we'd probably be much further down the track than we are. And I think we'd probably be on Mars in some sort of habitat by now, but I don't think it'd be as glitzy as it is portrayed in the show.
That's interesting.
Yeah, I'm just thinking that we'd be somewhat further down the track, but not to a great extent, would be my feeling on it. Simply because of the technological limitations that we would have faced.
Yeah. I've never seen For All Mankind.
Oh, you've got to check it out. It's so clever. Yeah, it's just an alternative history series.
No way. No way at all. all we are allowed to watch is Scandinavian murders.
Well, there you go. You've got yourself boxed in.
Scandinavian. Yeah, I'm boxed in by that. But I'm relying on you, Andrew, as my For All Mankind spy to keep me posted on what happens.
Well, I think the next season, because last season they ended up on Mars. This season, it's actually set in the future, and they are now going way beyond that, and it gets into the realm of asteroid mining and that kind of thing. So it sort of started with a bang because the Russians were first on the moon, and I don't want to spoil it for people who haven't watched the previous season, because there was a big revelation in that about who was first on Mars, but I can't do that. But it does sort of push the envelope in terms of human development in space technology, and it does sort of make you think, what if they did have unlimited resources? What if the world had taken a different attitude and a different approach to space exploration early on? Would we be that far down the track now? My feeling is not quite. We'd certainly be probably much better positioned to do these things now than we ordinarily would be, but I'm just not sure we'd be as far as that show indicates in terms of human successes.
Does the show does it imagine world peace, or is there still a political imperative to do better than your neighbours?
There's still a political imperative to do better than your neighbours, and it's sort of evolved into a race between the United States and Russia and the private sector. That was in the last season portrayed. The race to Mars was a 3-horse race, and well, it turned out to be a 4-horse race that nobody knew about. There was a sneaky phantom player in but I can't let the cat out of the bag for those who haven't seen it. But it's you basically had 3 missions heading for Mars at the same time, and I think in reality that probably wouldn't happen. Although we've seen it recently with the Moon, there were 3 missions happening around about the same time to the Moon. Involving the Russians.
Mars is much more likely.
Yeah.
Sorry,
I think the way Mars would, and we've talked about this before, I think the way to successfully achieve a human mission to Mars would be to collaborate rather than compete. I think that's where the difference is going to be.
I agree with that, actually, from my position of complete ignorance on the show. But I agree that I think it will be collaboration in the end, because it is such a major achievement to get to Mars. I was just going to comment though that the idea of people setting off to Mars at the same time isn't too fantastic, because the windows to get to launch spacecraft to Mars are every 26 months.
Yeah,
and if you miss one, you've got 26 months before you can do it again. So it's just because of the orbital geometry. But yeah, I think you've answered that far better than I could have done, Andrew. And so it's an interesting question, and I'm sure we would have advanced more rapidly, just because you could throw infinite amounts of money at the technology, and that would certainly refine things. But when you throw in that political dimension, though, you've got a whole lot of different aspects to think about.
Oh, yes. Yes, indeed. Thank you, Dylan. Our next question comes from Fenton.
Hello, Fred and Andrew. Enjoying your show as ever. This is Fenton in Minnesota. I have two related questions for you. One, is it possible to have two or more planets in the same orbit, for example, opposing each other? And what would have happened to Mars or Venus if this had been the case for us? Take it away, guys.
Thanks, Fenton. So I'll get you to explain opposing orbits first up, Fred, and then we'll get to the what if part of it.
I guess what Fenton means is planets on opposite sides of the solar system,
but in the same orbit plane.
And same. I think he means in the same orbit, actually, not
All
just
right.
the same orbital plane, but the same. We've already got that in terms of the Trojan asteroids that accompany several of the planets, including our own, around in the orbit of the Earth. So what you've got is stable points, the two, the fourth and fifth Lagrange points. I can never remember which one is ahead of the planet. So you can put something else at one of those Lagrange points and it will be stable.
Right.
And effectively, you get this scenario where objects actually orbit around those Lagrange points in the same way as they do, for example, as the James Webb Telescope and the Gaia spacecraft, as they orbit around the L2 Lagrange point, which is on the opposite side of the Earth from the Sun, about 1.5 million kilometers away. So, but that's not quite the same thing. The reason why I raise that is that it shows that you can have objects which occupy the same orbit as a planet, but they have to be in particular positions in order to be stable. I think that certainly the Trojan asteroids are examples of a problem where you've got two large bodies, namely for example, in the case of the ones in the Earth's orbit, you've got the Earth and the Sun, and their gravity mutually shepherds these much smaller orbits into those stable positions. So it may well be that if you put two equally sized planets, then there are different characteristics, and it may well be that you can only have them, for example, at the second Lagrange point or something like that. The third Lagrange point, which is on the other side of the Sun from whatever the planet is.
Yeah.
So it's an interesting scenario, and it certainly would have changed the dynamics of the solar system. The solar system would look very different with an object in it that was always on the opposite side of the Sun. There are some, conspiracy theories that say that that's the case, but it's not.
Yeah, I've heard that one.
Not. Yeah. And had it been the case for Mars and Venus, for example, we would certainly have had different sorts of observations of the planets. It's an interesting question, Fenton, and that's a waffly answer, but it's the only one I've got at the moment.
No, fair enough. All right. Thanks, Fenton. Lovely to hear from you. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Right now, new and current customers can get any phone for free at US Cellular, so you can connect with all your family members this holiday season. You can even call your aunt who always makes you talk to your cousin, who's a dog. Or, maybe just send her a festive text. Get the gift of connection at US Cellular. Get any phone free today. US Cellular, built for us. Terms apply. Visit uscellular.com for details.
We value human connection with fewer distractions. US Cellular, built for us. Visit your US Cellular authorized agent, Cellular Advantage, located at 918 South Locust Street in Glenwood.
0G, and I feel fine.
Space Nuts.
Now, Fred, we've got a text question from William. This is going to take a while to read. How does gravity make planets round?
That took quite a while, did that?
It did.
Yeah.
Sorry, I have to take a breath.
Yes, yeah. So what you meant was, how does gravity make planets round?
Yes, maybe I got the inflection wrong. But if I want to be really super technical, I should have said, how does gravity make planets spherical?
Yes, you should. That's right. And it's because if you have a fluid, and at the time that these objects became spherical, they were molten largely. So you've got a fluid, and what it wants to do is pull itself to a central point. That's what it's trying to do. That's how gravity works. It's trying to pull itself to some sort of central point. And because that's happening in all directions, this gravity pulling is isotropic, happens in all directions, then what you get is naturally a sphere. It's something that you see with bubbles of liquid in the International Space Station.
Yeah.
But it's not gravity that does it there. It's surface tension, but surface tension has a similar effect. It tries to minimize the size of the surface. And I suppose in a sense that's what the gravity's doing, but it's a rather different mechanism. So it's always pulling towards that central point, and that just makes it naturally spherical.
Just it's a natural state of being, basically.
It is, yes. For something big enough to have been fluid and for the gravity to overcome the resistance of whatever the is left whatever viscosity is left in the fluid.
The shorter answer, William, would have been because. Which reminds me, on the cruise last week, we loved going to a trivia section where if you couldn't answer the question, you had to provide a dad joke, and that was the fun part. Okay. Why did the chicken cross the road?
Because.
Oh.
I like that one.
Yeah, that's pretty good. Let's get an audio. Thanks, William. Audio question now from Chris.
Hello, Dr. Fred and Andrew. This is Chris Foley in the United States, just outside of Boston. Love the show. You guys are great, and it's my favorite podcast. Certainly my favorite astrophysics podcast. My question is not related to black holes, but antimatter. And I'm watching a documentary now, which is talking about the creation of antimatter through the decay of titanium-44. Now, I did not realize that antimatter I thought it could not be produced. I thought it was theoretical. Clearly, I'm wrong. But I was hoping that Dr. Fred, you could expand on antimatter and how it is created and how often do we see it. Thank you very much. Enjoy the show, and all the best to you guys. Thank you.
Thank you, Chris. Lovely to hear from you. Hope all is well in the Boston area. One thing I don't think we want happening is the expansion of antimatter. If we can expand on the idea, but not the antimatter itself.
So antimatter differs from normal matter in that it's got the opposite electrical charge. And that's why a couple of minutes ago we were talking about, when we were talking about turning energy directly into mass, we mentioned that the mass that was produced was electrons and positrons. So electrons have a negative charge, positrons are the same thing but with a positive charge. So it's all about electricity. It's about the electromagnetic force. And yes, there are ways of producing antimatter, not just the one that we described earlier in the show. It can be done in large colliders, large particle accelerators, because there are certain collisions and certain reactions that actually produce antimatter equivalents, which almost certainly, most commonly, they just annihilate one another, because that's what happens with matter and antimatter. They annihilate each other. So I'm not familiar with the process that that Chris was talking about regarding titanium-44 is an interesting one. I'll check it out. But it's not unusual for antimatter to be produced in these particle collisions. We believe that it was produced in the early universe as well. And one of the problems that cosmologists face in trying to explain the way the universe looks is why that today, as far as we know, we see a predominance of matter rather than antimatter, whereas the mathematics seem to suggest that in the Big Bang they should be created equally. Matter and antimatter should be created in equal proportions, but they clearly aren't, because we've got an imbalance. Like we are surrounded by matter, which is just as well, because if we were surrounded by antimatter, it would be a bit violent. So yeah, interesting, really interesting question about the production of matter and antimatter, but it's even more interesting when it gets to be a discussion about the origin of the universe, because it's still one of those unsolved problems.
I did find just a one-liner from back in 2017. Titanium-44 decays to scandium and then to calcium, emitting positrons, the antimatter equivalent of electrons in the second decay.
There you go.
So, yeah, it does happen.
Well spotted. Thank you.
I had to try. Okay, thanks, Chris. I think we dealt with your antimatter, which means we didn't answer the question. Next, we go to Nick, who's got a really interesting question, which, it's thought-provoking. I wouldn't have thought of this, but Nick certainly did.
Hello, Fred and Andrew. This is Nick Lindsay here from Perth. I have a question that takes us back to the moon, and specifically the description that we use of the lava flows on the moon. Now, lava tends to be very viscous, and in a low-gravity environment like the moon, or microgravity, I should say, I don't quite understand how it would flow. Should it just not pond or build up like Olympus Mons has in Mars? And the other thing is that lava tends to be full of gas. And should we not be seeing massive amounts of frothing, given that the gas is expanding into a vacuum? Anyway, those are just comments. Love the show. Carry on. Bye.
Thank you, Nick. It's a good question, because lava flows on Earth are subject to a 1G environment. The moon would have been quite different when it came to the situation with its molten activity, I imagine.
Yes, that's right. Because I mean, that's the number one thing that's different. The moon's only got 1/6 of the gravity of the Earth. But I think Nick is generalizing a little bit more than perhaps a volcanologist would. And in fact, the volcanologist who I know best is also called Nick Petford, formerly of the University of Northampton, and who has been with us many times to look at volcanoes in different parts of the world, principally Iceland and Hawaii.
I'd love to hang with that guy.
He's fabulous.
Volcano junkie myself.
Yeah, no, he's fabulous. Anyway, well, you will know if you're a volcano junkie that lava comes in different types.
Oh, yeah.
There's the A'a lava. These are mostly Hawaiian terms. It's basalt, doesn't flow particularly quickly. And the Hawaiians say it's called A'a because that's what you say when you walk on it in bare feet, because it's still sharp and got sharp points to it. That's a story, but it's a good one. Then another Hawaiian term, pahoihoi, or pahauho. It's a much less viscous lava that flows very, very readily indeed. And it's what you see splashing around. And that there's when Kilauea erupts, a volcano on the Big Island of Hawaii, that's what you see.
Yeah, it's also splashing around. It's also called lava.
Yeah, probably is. Yeah, but it's very, very liquid, very viscous. It would sort of settle down without too much fuss if you put it into a bucket. And then there's pillow lava, which is what you get when lava erupts under a water surface underneath the ocean. It's what you get forming under ocean vents. So but I think, as I understand it, the lava flows on the moon are principally basalt, which means it's going to be lava predominantly. But it clearly has enough of a flow to it that it can form these flat plains. It's what we see now when you look at those closely is you see it covered by the lunar regolith. You don't see the lava surface itself. It's got a soil on top of it that has resulted from erosion caused by micrometeoroids, caused by solar radiation, all of that stuff. So if it was frothy and bubbly, you'd tend not to see it. That would have been worn down, because we're talking now about lava flows 3.5 billion years ago.
Yeah.
They're not recent. Even though they look relatively smooth. I was looking at the moon last night through a little telescope, and I'm always blown away by just how smooth those maria, the lava plains, look. And that's an illusion. They're not. They're quite hilly and pockmarked with craters when you look at them closely. But on their large scale, they look very smooth. So I don't think there's an issue there. It's a good question, though, Nick, and I hope that helps you to answer it.
Excellent. Thanks, Nick. Lovely to get your question. And a reminder, if you do have questions for Fred, you can send them in to us via our website, spacenutspodcast.com or spacenuts.io. There's a couple of options there, the AMA tab or that little buttony thing on the right-hand side that's purple for some reason. Keep them coming. We've got a whole bunch, but we always want more. So send them in to us. Don't forget to tell us who you are or and where you're from. We love to know all about you, how many dogs and cats you've got, budgies, whatever. Sorry?
Goldfish?
Goldfish are very important in the world. Yes, I had plenty. In my life. Loved them. My favourite was a little one called Spot. He was cool.
Let me guess why he was called Spot.
Have a go.
Did he have a spot? He might have had a spot.
He had a white spot on his body, yes. He did. He was so excited every time I walked in the room. That's why I liked him. He used to just go, "Oh, Andrew's here." No, he actually probably was just going, food. Yeah. I imagine. But send your questions in and have a browse while you're there. Check out the shop, and maybe you want to become a patron. You can do that on our website as well, spacenutspodcast.com. Fred, that wraps it up for another week. Thank you so much. It was a lot of fun. Love the thought-provoking questions.
Here. Me too.
So I'll see you in a week, or less or more. Who knows?
I think I can manage that. I think that would be great. Yeah, let's do it, Andrew. Let's do it for a change.
Okay, just for once.
In a week. Yeah.
Thanks, Fred. Catch you later.
Sounds good. Take care.
Fred Watson, astronomer at large, part of the team here at Space Nuts. Hugh was unable to join us in the production booth this week, so everything went perfectly. And from me, Andrew Dunkley, great to be with you. Hope you can join us again on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.